Okay, so let's see how we can apply Newton's law to be able to set up differential equations of motion for objects that are experiencing different forces. So let's consider first a falling object that may be falling in a vacuum where all the atmosphere has been sucked out and there's no air resistance. Okay? This is the only force that it experiences is mass times gravity. So we use Newton's law to set up the equation by identifying all the forces acting on the object, and we use that for the sum of the forces. So in this case, there's only one force, the weight force. There's no other forces to add to the weight force, so that becomes by itself the left-hand side is equal to mass times gravity. Now, the way I've written my Newton's law here has both a positive weight force and a positive acceleration. Okay, so it's important to get your directions correct. Let's say going down, we can take as the positive direction, and then vertically we can take as the negative direction. Okay? So in this case, both forces are, the weight force is directed down and the acceleration of the object is down, so both vectors have to stay positive. Okay? Now the weight force is given by the mass of the object multiplied by the acceleration due to gravity. Mass times g. That's our result for the weight force is equal to mass times acceleration. So A is equal to G. Now, the next step is to set up our differential equation is recognize that A, the acceleration, is in fact a rate of change of velocity with respect to time. That's your dv dt. Okay? And so we can form dv dt is equal to acceleration due to gravity g. And from that, we get all our constant acceleration rules. Yeah? So this one gives you v equals u plus at, x equals ut plus half at squared, and so on. Okay? You get all your constant acceleration formula from that. So we apply do the same thing now, but for an object that experiences another force, maybe the force due to air resistance. So air resistance is such a force that it depends on velocity, how fast you're going. Everyone, you're driving. Your parents are driving you in the back seat, you wind down your window, you stick your hand out the window to enjoy the sunshine, and you can feel the pressure of the wind against your hand. And if you go faster, there's even more pressure against your hand. Yeah? Everyone relate to those experiences as a child? So the air resistance that you experience against your hand depends on how fast the car is moving. Okay? So the force due to air resistance is dependent on velocity, and in some cases, falling through air, it's velocity squared. Okay? So again, we start by using Newton's law. The sum of all the forces is equal to the mass times acceleration. Positive going downwards direction are positive forces, upwards are negative forces. So now we get mass times gravity being, we call that the weight force, going positive direction, so it's a positive term. But now we are going to subtract the force that's vertically upwards, the force due to air resistance. And this is k times v squared. K is just some constant amount that that number depends on certain things like the size and shape of the object, the texture of the object. In this case, a smooth object like a bowling ball will have a different k value than a tennis ball that has furry or hairs on it. Okay? So size, shape, and texture are the properties that create what are the K value. All right? Physics student will know that as the half pack V squared rule. Yeah? All right. So that is equal to mass times acceleration. Let's rearrange that to get an expression for acceleration by itself. Divide both sides by mass, and I get G minus K on M V squared. Okay? And now we're ready to set up our differential equation. Acceleration here is a dv dt, and so our differential equation now is the rate of change of velocity with respect to time is equal to G minus K on M V squared. Okay? And now we're ready to tackle such a beast. Okay? Let's think about how we're going to solve such a DE, a differential equation. So give yourself enough working out space in your book. Let's rewrite that one. Okay? So, firstly, we have two terms on the right-hand side. We're used to solving differential equations that are not adding terms or subtracting terms, but are factors multiplying. Okay? So, we want to have a situation where our differential equation takes this form, a function of x times maybe a function of y, so we're able to then separate our variables, our expressions involving our two different variables. Okay? So this is the standard approach for separating variables. That's the structure that the DE has to be. So in this situation so far we've got n terms. The first thing to do is to factorize one part out, to have two multiplying parts. Okay? So let's factorize first. Now, who'd like to suggest something that might be useful to factorize? Mass, good. M for mass, so take a factor of 1 on m out. What else? And k and the k value. So these two parameters, k and m, this fraction k on m, this is the parameter that determines the size, shape, and texture of the falling object. So let's describe what these parameters mean. Size, shape, texture, or the makeup of it. All right, all that goes together to give you a value which we're going to call k. All right. Then we've got m is the mass of the object, and of course g is the acceleration due to gravity. Okay, so given that, let's take out a factor of k on m out. So we get just v squared by itself, and that's good because now there's no other pronumeral multiplying factor in front of this pronumeral, and that's a good thing because we know in integration gradients of terms tend to come out as extra factors outside the integral problem, yeah? And we'll see how that occurs. Now, what will be left? What will be on this term? First we started with just gravity, then we factorize from this, take out, we divide a factor of k and m, and what will occur, it appears in that term as the reciprocal. Okay? So I'd like us to pause there a little bit. We're going to make a little bit more sense with mass times gravity times K. And think about what that means. Sorry? It's very similar to that. W, weight force, divide the size, shape, and texture constant of the air resistance. Yep. But let's see where these came from in terms of forces. Okay. Now, let's come back to the start again. The sum of all the forces was the mass times gravity minus the kv squared. Okay? Now, from that, I want you now to try and think about the situation before we can proceed with some more math. An object is falling through the air. If we drop it from rest, then the speed of the object is going to increase. What will happen eventually, do you think, in the long run, to the speed of the object? Very good. It's going to reach a point where it reaches a maximum velocity called your terminal velocity. And this is what skydivers do when they jump out of a plane. They spread out their arms and legs and open up their area, make themselves bigger. And so they fall towards the ground, but at some maximum velocity called a terminal velocity. Okay? So what we're expecting there, this is a little preview of what we expect on how the behavior of velocity is going to change with time. The pink line is how velocity increases with time without no air resistance. Okay? The black line is what happens to velocity with time with air resistance. It increases up to some maximum point. Okay? We're going to call that maximum velocity terminal velocity. So, if we get to some maximum constant velocity, what can we say about the acceleration on the object if its travel reaches some maximum constant velocity? 0. Acceleration goes to 0. So at max v, which we're going to call terminal velocity, okay, the acceleration is equal to 0. What is acceleration equivalent to? Rate of change of velocity with respect to time. Good. What did Newton say that acceleration is similar to or equivalent to? Well, of course you can come back to his famous law. We add up all the forces acting on an object, and that's related to a mass multiplied by the acceleration of the object. But if the acceleration is 0, then we get the sum of all the forces is also 0. Okay? So when we reach our maximum velocity, our terminal velocity, all the forces, the weight force and the air resistance force, they're going to balance each other out to be the same amount. And the sum of all the forces, the net force, is going to equal 0. Okay? So in that case, that's when we've achieved our terminal velocity. So mg minus k times v squared is equal to 0 at our terminal velocity. And when we get to our terminal velocity, then we're going to call our velocity, it's no longer going to be some variable changing velocity. It's going to be some constant velocity, which we're going to call Vt, standing for terminal velocity. So when it equals 0, our velocity is a v subscript t, terminal velocity. So what is terminal velocity? Let's use this expression. Terminal velocity is then we subtract the mass times gravity and divide by the k constant. Okay? So, and of course from there, terminal velocity is the square root of mg on k. Okay? So, this here, where is this term? That up there is what appears in our differential equation. Okay? So we're going to rewrite our differential equation in terms of, not in terms of mass, gravity, and our size, shape, and texture constant k. We're going to introduce a different term, different parameter called the terminal velocity to make it more convenient. Okay? So if m times gravity divide k is terminal velocity squared, then what about this factor over here? K divide m. What is k divide m the same as, do you think? Can we rearrange this for what, to get an equivalent form for k divide m? Well, I'll have to do the reciprocal. I'll have on terminal velocity squared, and then the gravity is now in the denominator. I have to multiply by the gravity. Onto the right, I'll have g on vt squared. Okay? Does that make sense? So there's an equivalent form there. So let's use that. Then our differential equation, equation number 1, okay, dv dt is equal to, our first term here is gravity divide terminal velocity squared. Okay, and then inside our bracket is mg on k, which is terminal velocity squared minus velocity squared. Okay? There's a slightly different form of the dE, just in terms of different parameters, with this important term, the terminal velocity parameter. Okay? So now we're going to separate our variables. So to do that, what do you think would be the first operation to rearrange our differential equation? Divide. What part are we going to divide by? The bracket. Yes, the whole bracket here contains the variable v. This bracket, that variable v there, we want to have on the left-hand side with the dv. Okay? So divide by the bracket, and we get 1 over terminal velocity squared minus velocity squared dv equals, and then to have the variable t on the right hand side, we're going to multiply by dt. We'll have g on terminal velocity squared dt. Okay? So now we've got all the v terms on this side and our t terms on this side. Even though we've got a terminal velocity squared on the right hand side with the time, this here, g divide terminal velocity squared, that's just some constant number. Okay? The only variables we have in this equation now is velocity, that's your variable, and time, that's a variable. Or small, or dv, small v, small t. They're your variables. Okay? All the rest are constants. All right, so now we're going to integrate. Now I've left a little space here on the left. Look at your denominator. You've got terminal velocity squared minus velocity squared, the variable velocity squared, okay? There are two quantities that are subtracting, that are squared and that are subtracted. Now, that there is a algebraic structure we know as the difference of two squares, okay? So, what's another way of writing that? So it could be plus the velocity, and then the second factor minus the velocity. Okay? And we separate into two linear factors in the denominator. Everyone see that? What kind of integration technique do you think we need to use now on the left? Partial fractions, exactly correct. Okay? All right, so let's do some partial fractions. So we have 1 over Vt plus V, Vt minus V. Well, we separate into two fractions. All right. Cross multiply. When we factorize v and terminal velocity out, we can get a numerator like so, yeah? Alright, so now let's equate our terms. So let's equate the v per numeral. There is none here, so that means b minus a is equal to 0. Then the a constant is equal to b. Alright, they're the same quantity. Everyone happy with that so far? All right. And then also, let's equate the constant with the 1. So an a plus b times terminal velocity has to be the same as what number? Constant number 1. Okay? Now to simplify that, we know that a is equal to b. So we can get 2a times terminal velocity is equal to 1, and so that a is equal to b is equal to 1 over 2 times terminal velocity. Okay, by solving for a, we divide by 2 and divide by terminal velocity. A and b are the same, so we can conclude both have this value. Okay? Alright, so let's put that back in and let's set up our differential equation again. It's going to become now past all that, let's look at our integral, put it back in. So we've got the integral on the left is, this becomes this one. So because a and b are both the same, then our separation of fractions, we've got the 1 on 2 terminal velocity in both numerators, and it's that constant 1 over 2 vt that we can bring out the front, and we'll have 1 over terminal velocity plus velocity plus 1 over terminal velocity minus velocity, and integrate that with respect to velocity, equals, and then on the right it's g on terminal velocity squared, and then if we do the integral on the right hand side, what does that become? So it's that constant times t plus c, the integration constant. Don't forget that bit. Okay? Good. Now, is there things we could do to simplify it a little bit? Are there any constants that we can divide on both sides? Yeah, there's an extra factor of terminal velocity. So this factor of 1 over terminal velocity, we've got another 1 over terminal velocity on this side. So just to make it a little bit more simple, let's times both sides by a factor of terminal velocity. So we get now a half of this integral okay, equals now g on terminal velocity plus c. Now, it's important to just note this integration constant here is actually a little different than the one above. How? How is it different? That's right, it's got this factor of terminal velocity that has been absorbed into it. Okay? Does that make sense? But because it's still a constant, it's okay to write it just as c, integration constant. Alright, so we're moving nicely. Let's keep going. Now that integral, what will that become? We've got half of the natural log good, and because we've got, and let's do it in 2 steps. So the first term, yep, the first term gave us that. The second term, yes, becomes a minus because we've got Vt minus V. So because we've got a gradient of -1 on the little linear part inside the log, that factor of -1 comes out the front of the log. Okay? Does that make sense? So, and then g on terminal velocity t plus c. Now we've got a subtraction of logs with the same factor of a half in front, so we can use a log law to collect that. Yeah? Okay, so from here we will have common modulus, keep it all in the modulus for now. Yeah? Very good. Now, what we want to now is start to, we can do 2 things. We can start to solve for velocity, and also we can, or at this point, think about what we're going to do about our initial condition to work out our integration constant c. Okay? So, here, what we're going to do now is think about an initial condition on the situation. So, in thinking about the initial condition, you can always do that relative to the diagram or picture you have. Okay? So in this case, an object is falling through air. Okay? If we consider the situation where the object is held and then dropped from rest. Okay? In that scenario, drop from rest, what are we going to say about our initial condition? When time is 0, our velocity is 0. Okay? So this is one scenario. Now, we'll also consider scenario number 2, where it's not dropped at rest if it's thrown with some initial velocity. Okay? So for now, let's drop it from rest. So at this point, what does our log become? Half natural log now of 0 and 0. So we've got, what's left is? 1. Terminal velocity divide terminal velocity, which is just the 1. Equals, time is 0, so that will go to C. Okay? So then, what is the natural log of 1? 0, that's right. That's great, we like this version. Okay? Alright. So, let's now push forward and speed it up a little bit. I'm going to multiply by 2 to the other side, and I get 2g on Vt times time.
Okay, so was it laptop stuff here?
It was taken already. Oh no, that one. Yep.
Taking my hoop. Marty?
Okay, guys. Are you heading off home?
I'm not heading.
Okay. So, what do we get next? Let's keep going and solve for velocity. So, now, we're going to think a little bit more careful about the situation involving the modulus. So keep the modulus for now. So the modulus of that fraction is then e to the power of 2g on Vt times time. Okay? Now, in this situation where we're dropping the ball from rest, velocity begins at 0, okay, and increases up to some maximum velocity, okay? So what can we say about the domain, or the range of values on V, we should say? What's the range on our velocity? Yes, 0 to the maximum terminal velocity. So since that's the case, look at our fraction, all right? What would be the overall sign of the numerator in that case? If velocity is positive, going from 0 to terminal velocity, then the numerator will be positive or negative? Positive, that's right. What about the denominator? It's also positive, that's correct. So overall, the fraction is positive. We can drop the modulus. Yeah? Okay, now let's multiply the denominator. Okay, and we're going to expand. Goal is to solve for just V. Okay, expand, and we're going to subtract this terminal velocity over here by itself. We're going to subtract that one over to the right hand side. So we get a Vt times the exponential minus V times the exponential. Okay, and I'm subtracting that extra terminal velocity term. Okay, now let's bring our velocity terms together. So I've got this one, and I've got this one over here on the left hand side. I'm going to bring them both together. So I have to add the term to the other side. G on Vt minus terminal velocity. Okay, now this terminal velocity is just some constant number, and it appears in two terms. So I'm going to factorize it out. And this velocity over here is also our variable that we want, and we're also going to factorize that out. So we have a 1 plus e 2g on terminal velocity is equal to, okay, terminal velocity, there's the E, understand? And to solve for velocity variable by itself, we've got to divide by this bracket. With this factor of terminal velocity by itself out the front, and in the numerator we've got one term okay, and then we did it. So that in fact is the first level of that function, the first incidence of that function where we've got velocity as the subject. Okay? So that there's a velocity of any object as a function of time. But it's not the best way of writing that rule. Okay? So the next step is a little bit of extended algebra to manipulate the function. Okay? So in manipulating our rule, we're now going to do some factorizing. All right? So we're going to factorize something. You might think, oh, what is there to factorize? Well, 2 g on velocity t. Is it a minus 1 in the numerator or plus 1? Minus 1. And then 1 plus. So we've got this bit. Now, first off, have a look at our exponential. In the exponent, you've got this factor of 2 there. Okay? So first step is to use an index law. That says if you take some exponential number, raise that to the power of one factor multiplied by another factor, multiplying powers, okay? Then that's the same as having a to the power of one of those powers or to the power of something else, okay? So we're going to do that to our exponentials. Hello again, Werther. So what we're going to do is take out that factor, that power of 2, as itself. So we're going to have e to the power of g on v t times time, all squared. Does that make sense? So each exponential is actually the same thing, but squared. Does that make sense? So because it's squared, there are two of them, two factors. Let's take out one of those factors. Let's take out a factor of e to the power of just g on terminal velocity times time from both the numerator and the denominator. So our velocity now becomes terminal velocity multiplied by let's first factorize it out from the numerator. So I've got two lots of that exponential in each term. So if I take out one of those exponential factors, okay, then I've still got one left in the term. Okay, but if I factorize it from the number 1, because there's no factor there, I've got to do a division of it. So it'll be minus 1 divide the exponential. I don't like writing it in fraction form, 1 over an exponential. What's another way I could write that exponential with a different power? Negative power, very good. So it's e to the power of negative g on terminal velocity times time. Okay? Let's do the same with the bottom. So I'm going to take out a factor of e to the g on vt. Alright. And then take out both from the two terms. Taking it out from whole number 1 gives you e to the power of negative g on v times time plus, and this denominator here is e to the two lots of the exponential, or the exponential squared. There we go. All right, we end up with that. So we get this nice structure. And what do you notice? Those two factors of the same exponential in the numerator and denominator that we factorize, they cancel each other out as a common factor. So terminal velocity times e to the g on v times time minus e to the negative g on v times time, and then in denominator we've got e to the g on v times time plus e to the minus g on v times time. So I've done is just swapped the order of my addition terms in the denominator. Okay? So I've got e to some power, subtract e to the negative, divide e to the positive power plus e to the negative power. That there is a famous, well, there's an equivalent way of writing such a rule. And we had explored such things in term 2 when we were doing application task. We're looking at the catenary shape and curve. Yes, correct. What kind of, Meshra, you can tell us more, what was the kind of function that would go towards? Cosh? Yes. Or, and? A sine? That's right. In fact, the numerator is a sine function, or the form of a sine function. The denominator is a cosh function. So overall, it's a tan. It's a hyperbolic tangent function. Okay? We end up with a hyperbolic tangent function. And we're going to write that as tan. And what goes into the function of the hyperbolic tangent is the exponent. G terminal velocity times time. Okay? And there it is, finished nicely. So what we're going to do is check some dimensions. Let's check some dimensions, which means look at the units of measurement of what's happening inside our tangent hyperbolic function. So we've got a g, which is acceleration due to gravity on terminal velocity multiplied by time. And we want to know overall what kind of dimensions that little expression has. Okay? So, for instance, what are the units for gravity, the acceleration due to gravity? Meters per second squared. Okay? So that's our dimensions of the gravity. What about velocity? Down the bottom here, it's meters per second. So if you do a per second on a quantity down in the denominator, where does that time unit, a second, go? It flips up and appears in the numerator. So that's meters per second, but the reciprocal of it, yeah? Because it's divide by velocity. And then we times time. So when we times by time, we're timesing by another second. So these are our units of measurements. And what do we notice? Well, the meters, the measurement of meters cancel out and measurements of time cancel out. So altogether, what we have as a quantity inside our tangent hyperbolic function, overall, it is dimensionless. Okay? It's dimensionless. So, which is a good thing, because you've got tangent hyperbolic of a dimensionless number times a velocity. Okay? So it's just some proportion, some constant number, multiplied velocity, and that's what we want, a velocity. Okay? Overall. Yeah, very good. So that there is the velocity of an object falling under quadratic air resistance.